Hopefully you're doing all right today. Let's get into the Ohm's Law notes. So here's the objectives for today. Explore the properties of Ohm's Law so you can develop an understanding how current and resistance are related. And you know you got it when you can uh, calculate voltage, current, and resistance using Ohm's Law. Now pictured in the top right here is George Ohm, and also he was a high school physics teacher. Equivalent to high school back then. All right, let's move on. Now, if you are in my class, you should have a document uploaded that looks similar to this that you can use to answer as you go through this. And these are the facts you need to know. If you're not in my class, hopefully your teacher has provided you the same or something similar. So remember, this is from our previous stuff about current, that static electricity is the buildup of electrons. And when we get enough electrons or charge built up, what will happen is the electrons will move from a region where they are built up to a region where they are not built up. All right, so what is current? The definition is the rate of flow of electric charges in a circuit. So if you look at these pictures, there are arrows. And if you notice, the arrows are going out of the negative end of the battery there, because that is the flow of electrons. So the electrons are going from the negative side to the positive side, flow of electrons. All right, just making sure you know that. And the amount of charge that flows per second is called the current. All right, so electricity can be symbolic of fluids, very similar, that there is a pressure difference that shows the beginning and the end of a system, and you can measure the amount of flow that passes per second. And circuitry basically works the same way. And you can measure this pressure difference or potential difference for circuitry as voltage, where the charge begins and ends. So current, which the symbol in physics for current is I, is the intensity of the flow charge. So current is your charge over time. If you remember, charge was previously shown by the letter Q and is measured in coulombs. So sometimes you might have a question that gives it to you in microcoulombs or something. Don't forget to convert it to just coulombs. And current is measured in amperes or amps. So a lot of times you'll see an A. You might see that on the back of something, electronic device you use that you plug in, possibly. Um, so coulombs per second is amps. So I equals Q over T. All right. So then what happens to the current when the same charge in the conductor passes in less time? So we put current, that's I, is our charge over time. Now here's two scenarios. So scenario A, if we have 4 coulombs in 2 seconds, well then our current is going to be 2 because it's 4 divided by 2. Now if we have that same amount of charge in less time, so 4 coulombs in 1 second, then our current will be 4 amps. So the current will increase or go faster. And sometimes you'll hear people say, you know, it's not how much the voltage is or something like that, how dangerous something could be, it's the amps. You might hear someone say that, and that is why this is happening. You are having more charge in less time. So something with a high amperage can be more detrimental, possibly. Now there are two types of current. One is direct, meaning it just flows in one direction. Should make sense, like a battery. And that's a lot of what we're going to look at. And there's also AC, which is alternating current. And so the current reverses direction many times per second. This is what you have in your house and your outlets. So this connects to the um, power station, that's within your area possibly. Now resistance. You should know what the word resistance is. In the context of circuitry, it's going to be what causes a restriction of electron flow. So the unit for resistance is going to be ohm. So you could put something called a resistor in your wiring, and that is going to restrict some of that electron flow. So now let's look at potential difference, or voltage, or EMF. So just talking about like with the water where you have that pressure differential, here you have a potential differential uh, from the positive and negative side of the system. So you'll have your, more electric charge on one side, or sorry, more electronegative charge on one side. And your electron flow is going to be going out of the minus side into the plus side. So the maximum potential difference is called the EMF, or electromotive force. Technically, it's not really a force, but whatever. And this is joules per coulomb. So that's your energy, joules per coulomb, that's your charge. And this is how you get voltage. So voltage, another word for that is potential difference, or EMF, and it's measured with V for volts. Now let's look at what Ohm's law actually is. Ohm's law is, by the quote, the voltage is directly proportional to the current when the resistance is constant. So again, voltage, volts, directly proportional to current, this is amps, when the resistance, ohms, is constant. And you can look, there is the equation on the screen, V equals IR. So R is going to be resistance, this will be our constant. So if you were to do a graph of this, then you would have voltage divided by the current, and that will give you your slope, which will be resistance. So resistance is constant. It's going to be a linear slope. So now looking at power. Power is the rate at which work is done. So this is something your parents hate, having to pay for all the time, because you leave your bathroom light on or something, or you leave your TV on when you fall asleep at night. I don't know. One of those things is causing their electric bill to go up. So the way we get power, there's actually a lot of ways to kind of work through this, but let's look at the simple equation. If you look near the middle where the text turns red, P equals IV. P is power, I is current, and V is voltage. So volts are joules over coulombs. This is back at in the blue box. Volts is joules over coulombs. I, which is current, is coulombs per second. And then when you multiply these out, you can see that there is coulombs that cancel out, so you end up with joules per second gives you watt, which is power. And if you notice, because there are three different variables in there, you have joules, you have coulombs, and seconds. There are three different variables, and you only need, you really only need, we'll see in a second in the next slide. You only need some of those to figure out exactly what you're getting, to figure out what power is, if you are already given the volts or the current, the amps. So if you look at something in a battery and it says it's a 9-volt battery, and you're saying, well, I have volts and I want to know how much, you know, if I have my resistance or something. We'll see in the next slide. I'll show you what I mean. So P equals IV. Power is current times voltage. And if you're looking at the units for this, this would be watts is equal to amps times our volt. So now here's what I was trying to get at on the previous slide. There are several ways you could actually get power. So power, using Ohm's law, we could substitute a few different things in here. So if you remember, V is equal to IR. So if you have I times IR, so I times V or I times IR, then you get I squared R. So that's how you get your second formula. So the first formula was already given, which is P equals IV. Second formula is if you substitute in IR for V. And the third formula, resistance, you can get by doing current is volts over resistance, and stick that in, and you get volts squared over resistance. So power can be calculated 3 different ways. And if you want to find the energy, so energy is going to be power times time. And because of that, you'll have your equation. I squared, so your current, your amps squared, times your resistance, R, times time. So I know there's a lot of these formulas we've just gone over. I know it can be confusing, so you might want to pause the video, slow down, or make sure you have these written down in the note sheet that was provided online if you were to print that out or write it out yourself maybe. So energy can come in many forms as well. Heat energy, light energy, any energy. And don't forget, all this stuff must be in standard units. So time is in seconds is the standard. Don't forget that. Energy is in joules, etc. So you might get a problem that might mention kilojoules. Well, don't forget, kilo means 1,000, so you got to do some extra math there. You might get something that says, hey, in 15 minutes, how much is blah, blah, blah? Well, you got to remember to convert that minutes, multiply it by 60, because there's 60 seconds in a minute. Now, fuses. Fuses are important for circuitry, for wiring, etc., because it controls the amount of current through a circuit. If there is too much current coming through, fuse, it'll blow, current's cut off. And you can have a interrupter, ground fault interrupter, which is a switch. You can go and you can reset it. You might see those in your wall. There should be one in your bathroom usually, and kitchen. That's typically where you might see something like that. And the reason for that, I believe, is probably just because there's a higher chance of water getting in there and then causing too much of an issue. All right, so how is the power in a circuit affected when the current is tripled across the same resistor? So we're talking about power, resistance, and we're going to triple the current. So which formula do you use? You got P, I, R. Well, we have this formula, P equals IV. Don't forget V equals IR. Substitute that in. You will get P equals I squared times R. So now we are going to triple our current. So what is going to happen to our power? Well, because current is squared, our power will be increased by 9-fold, 9 times. All right, an electric heater. Here's another problem. Electric heater requires 1,000 watts and is plugged into an outlet that has 110 volts possibly. So what is the resistance of the heating coil? So which formula are you going to use? Well, we have P, we have V, and R is what we're looking for. So we have power, which is watts, we have voltage, volts, and we're asking what the resistance is. Well, if you go back to your formulas, P equals V squared divided by R. So we have 1,000 for our watts. Our volts is 110, so we're going to square that divided by R. Now, of course, here, this is a inverse rule, so switch those around. R equals our 110 volts squared divided by our 1,000 watts. R should come out to 12 ohms. So that little symbol looks like a horseshoe almost. That is ohms. So here's another thought. So P equals IV. Once again, just throwing that out there. If you increase the voltage by 2, you only need half the current to deliver the same power. So if you send half the current through the same wires, you only lose a quarter of the power. And so that is with the same resistance, I should say. And you can see that equation can be solved by P equals I squared times R. So that's why we have high voltage wires to transmit electricity. So some more on resistance. Tungsten has a very low resistivity. It is a metal. It's a good conductor. Cell membranes have high resistivity. That is because most cell membranes are made of lipids that do not have metallic groups necessarily attached to them. So the human body has a pretty good natural resistance, 500,000 ohms. However, salt water, salt is sodium chloride, NaCl. So the Na part, sodium, is actually a metal. Most people either don't realize that or forget that. And that is actually going to be a good conductor for electricity. So if you are soaked in salt water, if you're swimming at a beach or something, well, then your resistance will go down a lot, 100 ohms. So it says stay away from salt water in an electrical storm because current above 0.15 amps disrupts the electrical activity of a heart, and then you might need a defibrillator or something like that. Now, distilled water by itself, just H2O, actually does not have good conductor properties. It has high resistivity. However, most of the water that we drink and everything has particulates in it, and all you need is a few of those particulates thrown in, and then it becomes a pretty good conductor after that. So water coming out the tap from your sink is going to have little metallic ions scattered throughout it. All right, so here is a wrap up. What are the variables and units for each of these things? Yeah, we went through all of these in this presentation. So charge, current, resistance, potential difference, power, and work and energy. So current represented by I, and the units are amps, or A. Resistance, which you will see most of the time with a R, sometimes with the ohm, and that is the unit, the ohms. Charge, Q, sometimes you'll see that as a capital Q as well, and that is in coulombs. Voltage or potential difference is in volts with V. Work, represented by W, is in joules. It's energy. Power, which is P, is represented by P and is watts, W. Time, little t, is seconds, which usually use S for that. And then energy is also going to be joules. Energy will be shown by E.